Welcome to the method of undetermined coefficients complications. So recall if we have an equation a y double prime plus by prime plus cy equals f of x, and the method of undetermined coefficients has us assume that yp, our particular solution, takes a similar form to f, just with unknown coefficients. So for now, we're going to focus on the equations where f of x is equal to e to the alpha x times a polynomial p of x, where p is of degree n. So for example, we might take the equation y double prime minus 2y prime minus 8y is equal to e to the 3x times x squared minus 4x. So that left-hand side has constant coefficients. The right-hand side is a e to the something x times a polynomial, in this case of degree 2. The question becomes, what degree terms do we need to include in our guess? So in our example, we just had a e to the 3x times x squared term and an e to the 3x times 4x term. Do those terms alone work, or do we need to include others? So let's just consider the term e to the alpha x times x to the k. Right? When we differentiate, when we take the first derivative of that term, we would wind up with an alpha e to the alpha x times x to the k plus a k e to the alpha x times x to the k minus 1. And when we take the second derivative, of e to the alpha x, x to the k, we would wind up with an alpha squared e to the alpha x times x to the k. We would wind up with two terms of the form alpha times k times e to the alpha x times x to the k minus 1. And then we would also have a term that was k times k minus 1 times e to the alpha x times x to the k minus 2. So note, when we go to plug in our guess, whatever terms we have, once we take the derivatives, we will also introduce lower terms. So what happens is when we plug in our guess, for yp into the equation, we will introduce all terms of sort of lower degree, right? So we will introduce lower degree terms. And so in order to be able to match the coefficients in our equation for the plugged in YP side and the right-hand side of the equation, we will actually need to include all degrees in our guess. So in order to match coefficients, we will need to include all terms of degree n or less. So our guess essentially would be YP is equal to e to the alpha x times an AN x to the n all the way down to A0 x to the 0, or A0 on its own, our constant term. So when we make our guesses, even if the original polynomial just had a degree 2 term and a degree 1 term, our guess will need to contain all. So if we go back to our example, I'm going to give myself a little more space. So going back to our example, so y double prime minus 2y prime minus 8y equals e to the 3x times x squared minus 4x. Our polynomial has degree 2. And so our initial guess would be that YP is equal to e to the 3x, matching that e to the 3x we had, times an A2 x squared plus an A1 times x plus A0. So this would be our initial guess. When we go to differentiate, the first derivative would have an x and would actually still have a degree 2, degree 1, and constant term. And the second derivative would still have a degree 2, degree 1, and constant term. And that will allow us then to force the equation to work out when we plug it into our differential equation. Technically, we do have a constant term here. It just has coefficient 0. And so we can match the coefficient in front of x squared, the coefficient in front of x, and also match that constant term. And we have 3 unknowns and 3 equations. We should be able to solve it ideally. All right, so here is where our complication can come in, where that ideally comes into play. So what if y equals e to the alpha x is a solution to our homogeneous equation? So what we're going to do is this winds up causing some complications. Some complications with matching the x to the n term. So when we take the derivatives, if we look back at what happened to our e to the alpha x to the k term, right? We never went up a degree, right? We stayed the same or went down in terms of what terms were included in each of our derivatives. So the only term that can result in an x to the n term in either of its derivatives is the x to the n term. So note, the only term in yp equaling e to the alpha x times an x to the n, going all the way down to a0. The only term in that which yields an e to the alpha x, x to the n term in any of its derivatives is the e to the alpha x, x to the n term. So we're just going to focus on that. So we'll just write yp is equal to e to the alpha x times an x to the n I'm not even going to, we'll do e to the alpha x times an x to the n plus a bunch of stuff of lower degree. That first derivative then would be, we would have an alpha e to the alpha x times an x to the n. And then we would have a e to the alpha x times n times an x to the n minus 1 plus a bunch of lower degree. And so we're looking at alpha e to the alpha x times an x to the n plus a bunch of lower degree. So anything I'm doing dot, dot, dot is lower degree. So we have our y prime just has that one x to the n term. And then similarly, if we take our second derivative, we would have an alpha squared e to the alpha x times an x to the n. Then we would have a plus alpha e to the alpha x times n times an times x to the n minus 1 plus dot, dot, dot. And so we get our second derivative also just has one term, x to the n. So we have an alpha squared e to the alpha x times an x to the n plus a bunch of lower degree terms. So if we plug this into our equation, so plugging into y double prime, or sorry, ay double prime plus by prime plus cy equals our e to the alpha x times some polynomial of degree n. So we would have a pn x to the n plus, again, a bunch of lower degree terms. Then what we would have would be, we would have a times alpha squared e to the alpha x times an x to the n plus our lower degree. Then we would have plus b times alpha e to the alpha x times an x to the n plus our lower degree, plus c times e to the alpha x times an x to the n plus our lower degree. All of this should equal e to the alpha x times pn x to the n plus our lower degree. So we can rewrite this left-hand side. We can pull out the e to the alpha x and an from our high degree term. And we have a alpha squared plus b alpha plus c all times x to the n. And then we would have plus a bunch of lower degree material. And this should equal e to the alpha x times p sub n, x to the n, plus a bunch of lower degree. But note, we assumed that y equals e to the alpha x was a solution to ay double prime plus by prime plus cy equals 0. What that means then is that alpha is a root of ar squared, or a solution to ar squared plus br plus c equals 0. And so that means that a alpha squared plus b alpha plus c is equal to 0. And so what we get is this whole x to the n term is just 0, and we therefore cannot match the coefficients, right? So what we have then is the x to the n term has coefficient 0, and so we cannot match the coefficient Pn. So in order to account for the fact that we lose our highest degree, the trick is to just raise the degree of every term of our guess. So to counteract the fact that our initial guess has its highest degree canceled out in the equation, we multiply our guess by x to raise the degree. And so what we get is if e to the alpha x is a solution, okay, let's summarize. So if we are solving the equation ay double prime plus by prime plus cy equals e to the alpha x times pn x to the n plus all the way down to p0. Then what we have a few cases. If e to the alpha x is not a solution to ay double prime plus by prime plus cy equals 0, then we guess that yp is equal to e to the alpha x times an x to the n plus all the way down to a naught. If e to the alpha x is a solution to ay double prime plus by prime plus cy equals 0, then we guess that yp is equal to x e to the alpha x times an x to the n plus all the way down to A naught. So we've raised the degree of every single term by x. That way we still will have n plus 1 coefficients to solve for n plus 1 equations for matching our coefficients. And then we have one more case, which I haven't gone through. It turns out if e to the alpha x and x e to the alpha x are solutions. So in other words, if alpha was a repeated root of our characteristic equation. So if both of these are solutions to ay double prime plus by prime plus cy equals 0, then we actually need to raise the degree one more time. Our guess will wind up being that yp is equal to x squared times e to the alpha x times an x to the n plus all the way down to a naught. So we actually need to know our solutions to the homogeneous equation. We need to solve that characteristic or find the characteristic equation, find its roots before we can determine precisely what our guess would be. So we have sort of the most simple case where we are not, we don't have a solution included in our guess. So note in this case that the lowest degree term, the a naught e to the alpha x, becomes a solution if e to the alpha x is a solution to the homogeneous equation. The a naught e to the alpha x would also be a solution, hence the multiplying by x. And if e to the alpha x and x e to the alpha x were solutions, then the a naught e to the alpha x and a1 x e to the alpha x would also be solutions, hence having to knock up 2 degrees so that no term is actually a solution. So in the next video, we will do some examples of determining what our base guess should be. And then in the final video, we'll actually work through solving for our coefficients.